Oh, what a day! What a lovely day!
Welcome to Flat Earth Debate. I'm your host, Nathan Oakley, and if you're new to this channel, or you've not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. If you would like to support this channel, there is a super chat that runs alongside each of these shows while they're live, and there's also a link in the info box below the video once it's rendered. Most importantly, if you would like to join the discussion, simply mute the page you are currently watching, then click the link in the info box below this video to join the panel and express your views on the shape of the Earth. If you do join, please don't swear. If you do, you'll be ejected, and if you are, please don't try to rejoin the stream using sock accounts. You'll be warmly welcome back on the next stream. Please also share the show. Sharing the show increases the live audience, of course, but this in turn increases the chances of a more diverse panel. So please share the show. And one last time, if you're new to the channel or you've not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. Now we are joined by Ranty Flat Earth. How are you doing?
Doing good, thank you very much.
Excellent.
How are you? How are you?
Very well, very well. No complaints. So what have you been up to, Ranty? What have you been doing?
Just doing more observations, I suppose. Trying to get in the right position to film the wind turbines. And I went down to the mirror ball today again. Obviously, I saw Barrow and Furnace, etc. You know, that kind of stuff. The normal stuff that you see on the flat Earth. We've also been working.
My kid's noisy toy off. Sorry.
All right. Well, yeah, and I came back and we had a bit of a discussion this morning. We did some workings out, didn't we, with these turbines? We might have something to present, I suppose. What do you think?
Yeah, let's just have a look at them and start talking through them, I guess.
Okay. Right, let me know when I'm presenting.
You are?
Okay, so I know we're going to go over this again, which is the compression of the bolts that seems to happen in a very narrow band. Essentially, the shape of the bolt, which is outside of that narrow band, stays the same. So obviously, this top of the bolt has been cropped out and superimposed here. And as you can see, it matches up with the bolt underneath. This is the full high version where you're seeing all of the bolt, obviously. Clearly make out stena line with the orange at the bottom. And again, this is all of the bolt. It's just been compressed. We've got the orange line that runs underneath it. We've got all the wording stena line, but it's been compressed into a very narrow band. So obviously that's what your optics do. That's what your vision does and what the camera does. Your eye cannot resonate into a very, very narrow band. It won't pick up all that information. It has to compress it. And this is what we're seeing on a lot of this stuff. On another day, this was a different observation of the same bolt. The top image here is a bit clearer, so you can see all of the orange that runs underneath. So again, we know we're seeing down to the hull. Now, Black Anthony Riley says they would blink test this generally. You know, they would take this bolt here and superimpose it over this bolt at the bottom and say, well, the bottom part of the bolt is missing, you know, proof of curvature. No, well, what we're finding with diligent experiments and diligent observations and analysis is that compression is a very real thing at the horizon. And we're starting to understand this now. We're starting to find the trick as to where this, why this happens. We have another boat that this is the Sea Truck Panorama. Again, the length of the boat is the same. The only thing that's different this time is the entire boat seems to be squashed. It's half the height of the boat normally. So obviously all of this boat is sitting in the compression zone, so to speak, and it's been squashed down. You know, this isn't an accurate representation of the boat, which is underneath. This is a very good image. This is a very squashed image. Just optics, what happens when you're looking over great distances. The atmosphere does this. Again, they would blink test this. They could superimpose this boat over this and say that this is proof of curvature. But you can tell that the height of this letter C, etc., and the actual wording on the sea truck is comparatively smaller than normal. Anything to add, Nath, at this point?
Well, yeah, I wouldn't say it was atmospheric. So at this stage, I would say that what you're looking at is a reduced viewing angle. And the only time it could be classed as atmospheric would be if you were to look at something like a wave in the near foreground crossing the midpoint. Whereas what we're talking about here is the circle of confusion, dirty air, whatever you want to call it. That area is an effect that mirages things up, and we've seen this in small scale with Zachary Sabala, Good Times for All, GUDTIMS, number 4, ALL. So Zachary Sabala has also shown this over a, let's just call it atmospheric neutral, if you like. So it's an air-conditioned building, and he shows this effect of things basically reaching the point where the viewing angle is too narrow to see them. You know, it disappears to nothing because the viewing angle also disappears to basically nothing as things get further into the distance. And as a net effect, you lose something from the bottom up. As it gets smaller, the angular size reduces and it gets closer to the horizon, to the point where, as you're looking down a turbine, for example, the bottom of the turbine obviously has a narrower viewing angle than the top. Therefore, you will lose the bottom first.
Yeah, we'll get to that in a minute. And this is what we're seeing with the observations from Barrow in Furness, different observation heights and distances. But we're seeing the same sort of thing. It's a compression of the image. It's holding its width, but it is being compressed. It's certainly not going over the curve. Now, bear in mind that these should not be visible from these observational points. Everything from this image down here to the bottom should never have seen these buildings. So the fact that we are seeing them over a vast expanse of water, at least in this location, proves that there is no discernible curve that can be found. Either that or it's looming every single day, because I capture this every single day. So more compression. Let's have a look at this this image here, right? So this is the wind turbines. We've got Barrow on the left, and we have Ormond on the right. So two sets of wind turbines. And from this particular angle, when I took this image, there is absolutely no change at all in the angle between the two farms. Now, you'd expect that because there's a vast distance between the two. This wind turbine here, this large one from Barrow, starts at 12.9 miles away. And the last turbine here, I believe, was 23 point... Hang on, let me get the measurement for that. 23.6. So this last one is 23.6 miles away, the very small one in the back of Ormond. And this one here is at 12.9 miles away. Now, this exponential curve that we should be seeing over that kind of distance, if we put a straight edge over here and we get it lined up, so these are in a straight line now. It's running through the top of the hubs. Let me just move this out of the way so that you can see. So now we have the angle. If I just drag that across and place it over the top of this one, we have the same angle. Exactly the same angle. There's no difference between the two. Same angle, same angle. Now, what does this prove? Well, it proves that there isn't an exponential curve. Would you agree with that, Nathan?
Absolutely.
Because
the ones further in the distance, according to the curve maths, are further round a curve. So while in isolation they may only have a couple of inches between them in terms of their relative curve to themselves, we are viewing them at 20 miles plus. Therefore, they need to be more severely curving than the picture on the left. The left one has the same amount of quote-unquote curve, even though it's a straight line. You can't have a straight line if it's curved. It must be curved. It isn't. It's straight, and they both match. They're both falling in line with perspective. That's all they're doing.
Can't disagree. That's just what the evidence is showing. You know, I mean, people are welcome to come down here and take the same observations as I do. The turbines themselves aren't going to change. The wall that they stand on to take the observation isn't going to change. This is just what we see. So, like I say, anyone's welcome to come. Alk, if you want to come down and take an observation of these turbines, you can go and do the exact same, and you'll see the exact same thing. So we have the same line, basically exponential curve. You would expect to see an exponential curve on these ones. So it'll be a different viewing angle than the one we actually have just presented here. What we've also been working on is from the same image. Now, this is quite important, and it might take a little bit of time to explain. So if people just bear with me, and they might understand it. I've tried to work out how the angular size has happened, the angular size change between these turbines, right? So this turbine here on the right is 12.9 miles away, and the turbine on the left is 15 miles away. Now they're equally spaced apart, 0.3 miles apart, these particular ones. So there's it should be a consistent change, and this is what we see when we look at the yellow line that I've put through the top of them. We have a very consistent fall. Nothing drops off. There's no bulging. And also with the good point with this observation was that I was able to capture above the mucky air this refraction layer. So the very bottom line, this one with the red part and the yellow, is a mirage. So this underneath here, where I'm putting my cursor now, is a mirage of this straight above it, and you can see that it runs through the image. So like this part here, this black part is reflected here, same here. So this is the refraction area. So above that proves that we're looking at these turbines at a height that we're able to gauge stuff and work things out and do some workings out. So we have this orange part of the turbine, which is all on all these turbines. It's at the bottom of the turbine itself. And above that, we have some numbers. It's very hard to make out, but they are actually numbered. These have got little numbers just above that orange part. So we can clearly see these. So we can use these as a gauge to try and figure out the angular size change between each of them. So I've run the line through the top of the hub, and I've run the line through the bottom of the hub of the turbine, but in a direct line where this orange is. So now we can see the angular size change between the two, the relationship between the two. So the difference between this point at the top here and this point here is greater than the distance between this point here and this point here, and that's the angular change of it. What's interesting is that after we've just talked about this compression issue that we see with the boats, is that as we follow along and we imagine that there was a whole row of these running throughout the entire image. So at this point here, this is the horizon line in the middle, the red one that I'd showed you before. And this is the angular size change of the bottom of the top of this orange part of the turbine. So I've lined it up, put it to size again. And what you find is that this angular size change pushes the turbine into the horizon. So we know that we can't see optically below 0. So if we're looking directly out and we call that 0 degrees, so level is 0 degrees, this essentially here, where this line here, this orange line, top of the orange line, intersects with the horizon, this mirage layer here, if we follow that, it actually intersects at this point here. So there's ground zero, so to speak, or eye level 0. That's it there. So with the angular size change of these turbines, right, and now this part of the turbine has already gone through this ground zero, eye level zero part here. So your optics and the camera can't resonate through that. It can't see below 0 degrees. It can't go and look through the water, because that's effectively what we're trying to do. We're trying to squash all this information for this turbine into a 0 degree angle where this horizon is here. And that's what we're seeing. So we'll follow the angular size change all the way through, So we're still putting the orange part of it on the angular size change here and to the top of the hub there. And you get things like this. This is the horizon line. And you get the hub that sits out of the viewing angle because you can see it. It's a wider angle to look at. And if you imagine the blade was turning, exactly how we see it. It's all disappeared from the bottom up simply because we cannot see through 0 degrees. It's just what happens. Now, this is, going back to this start of this image, this is all done through the angular size change. This is not done with any effects of curvature. There's a straight line through the hubs, proving no curvature. There's a straight line through the top of the orange, proving that we're running in a straight line but getting narrower as we go. And it intersects the horizon. There's no denying that that's it. This is what happens. We follow the lines. It dissects the horizon. This is the horizon line here. And it's very clear from the evidence that we're doing with these turbines that this is the effects of what we're seeing when we film these things, these turbines that seem to be cupping the water, and all that's happening is that the angle, we can't get all that information into 0 degrees. It just doesn't fit.
Right.
It won't
so
go there.
The further you go away from something, the more it gets small. Simple perspective.
Yep.
And as that angular size reduces, there is a limit to what you can physically see, and it will go beyond the vanishing point. As much as people want to assert that you can see forever, there is an angular size limit to what you can actually see. And when it reaches that angular size limit, it dips into this layer. Now, we currently call it two things: dirty air and the circle of confusion. And I think today we've come to a consensus amongst ourselves that what we're seeing in terms of this mirage layer, so if you can just zoom in on turbine 3, please, Ranty, you can see that there's these black lines, if you can get them all on screen, that are very thin bands, but on, it's actually turbine 2, you can see that it's right in the middle of the refraction layer. Now, I don't know if you've got anything you want to add, Ranty, because I want to play Zach's video if you're temporarily done.
I think I'm done. I don't think there's much more to add. Essentially, I've also lined it up with the numbers. So at the top of the numbers, I've put the line in through that.
Wait for that, because I want to come back to that. I knew you were going to that next. I know we've talked this morning. So, but before you do that, I want to play Zach's video. So I'm going to do that first, if that's good by you.
Yeah, sure.
Hello, everybody out there in YouTube land. Good times for all here, or Zachary Zabala if you prefer. We are at work again, and I did a little bit something different this time. I measured that. It's an 11-inch piece of paper. I made a mark every inch. You have two lids here, one the circle at the bottom, one the circle at the top, and I was wrong about my measurement last time. It was not 170 yards. It was actually 160 yards down to that other end. Like an idiot, I took people's words for it. So I measured it this time myself. And from the lids here to the farthest marking that I take a picture from, it will be 153.3 yards away. I did that by 20 feet increments. I will be taking a picture every 20 feet. So tomorrow I'm hoping to get the exact height of what the Sears Tower should be, the Willis Tower, from this distance at this, to scale perspective. And we're going to see how much of the bottom gets taken off. But today we're just doing a little preliminary, and we're going to see what happens. So every 20 feet, I should be taking 23 pictures, I believe. And then at the end, I'll do one from eye height, which is roughly about 5.5. I'm going to have to get a tape measure out and see that one. But that probably won't be today. That'll be tomorrow. But yeah, I hope you all enjoy this. We're going to see what happens. Oh, and I also wanted to mention one other thing. See all these lights here? They're all the same height. You see them down there? All those lights, they're not getting any lower. It's all about perspective, people. It looks like these lights are going down, 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 down. And then they set over those, you know? Nothing is setting, it stays the same height. It's all about perspective. And then once you get so low to the ground and so far away, you'll see what happens. So I hope you enjoy this. This is experiment number 2 with diffraction. And I'll see y'all down here at the other end. Alright, folks. I'd have to say all in all this experiment went pretty well. I'm not going to take too much time on each picture. Not until around 200 feet from 1.5 inches off the ground do you really start to see some good distortion. I mean, you can see it earlier, about 100 feet, you can start to see it. If I would take that blue line out of there, it's a very slight minimum. It was a warmer day on this day. I'm learning. I've done a couple experiments on this since this one, and I was able to actually see more than this one showed. So I believe diffraction is caused by the amount of humidity also in the air. The more moisture and humidity in the air, the more it has to look through and the more the objects get distorted. And of course there's more humidity near the bottom, as the heavier water molecules and whatnot would be sinking. It's really interesting, folks, how all this works, how our eyes work. As you can see, the bottom is getting harder and harder to make out now, and they're starting to actually converge, the two circles from the mirroring effect. The mirrored one on the bottom is actually starting to combine with the actual image. So this is what we see why the bottom of buildings are always missing from long distances. It has nothing to do with the curve of the earth. It is never the actual amount that should be missing, and it's usually very far from it. So, I mean, this is just how our eyes work. The bottom of things do disappear over distance. And then as you watch, here in a second, I'm going to go to eye level. There's about 3.5, 4 inches they're distorted.
Now before he does, I just want to keep it on this image for a second here, Ranty, so we can discuss what we've got on screen now. So obviously these paint cans, we now have a new horizon. It's got a blue line that's drawn in, exactly like you, above what looks like the horizon. Now with the poles, there is an effect of the miraging of the poles towards the new, artificial, false horizon, which is the bottom line in this image. I'll just wave my mouse over it. So that is the horizon for your image in the turbines, which we'll go back to in a minute. This second section of the paint can, obvious because it's circular, is not distinct when you're looking at the wind turbines, but in essence we are losing the bottom section of this, but before it disappears we see it mirage to the new horizon line. So that's exactly the same effect as we see in the turbines. That's why I pointed out that black section. I'll just let last 30 seconds of this video play, Ranty, and then I'll...
Yeah, sure.
Then I go back up to eye level right here, and boom, you can see the whole thing again. So all those people saying that, oh, it doesn't matter how high you are, if on a flat plane you can't see more, blah, 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 they're wrong. Flat out wrong. So this is good times for all, everybody. Signing out.
There you go.
Yeah, I remember watching that a long time ago. It must be out about a year, that video.
But what he's
I
demonstrating...
know Anthony was very happy with it first came out.
What he's demonstrating is how you get obstruction from the bottom up on a flat surface. And it looks, from the optical distortion that you get, like you have a new horizon line, and in the case of these turbines, they are being stretched down to an artificial point below where they actually are. And this is purely down to the angular size reduction and the reduced viewing angle. So we have a reduced viewing angle at the bottom, smaller angle at the bottom of the turbines than we do at the top as you look up them. So the analogy I tried to give to Ranti earlier was, if you were out at this distance, you're standing by one of these turbines and you take your shoes off and leave them there and start walking backwards, eventually they will reach this band, this miraging band, and disappear. However, if you then got your mate who's standing next to your shoes off camera to go and put them on in exactly the same position, you would see his ankles miraged and the rest of him exactly as he would be normally, because you have an increased viewing angle to him. He's physically larger. He has a larger angular size than the shoes, but the shoes are still gone. They've disappeared bottom first because of an angular size reduction. The angle is too narrow to see those shoes, and the same applies to these. They are too narrow at the bottom at distance to be seen. They will disappear bottom first as a result of perspective, and we will see, exactly as we did in Zach's video, a mirage line, which we have, and it is my opinion that we have a clear enough day to get this effect. So you will only see this circle of confusion, dirty air, this band that has the exact same replication underneath it as above it. This band is because we have a clear enough day to see it. So the wind and rain or whatever is all dispersed. We don't have enough distortion to not see it. So we're not having waves intersect the midpoint. These are close enough to see this effect without it being interfered with by waves crossing the midpoint. So you are actually seeing the point of convergence in this effect. And the reason things disappear from the bottom first is because they have a reduced angular size at the lowest extremity. That angle obviously increases as you look up the pole, therefore you can see the top half and not the bottom half as it goes further into the distance. Would you agree?
I would definitely. And also the fact that on this day, we have a couple of things that we could do the measurements from. Obviously, we've got the top of the turbine, the hub, which is very, very visible. But above this circle of confusion layer, this horizon line, this fake horizon line at the bottom, isn't the real horizon. This is the real horizon here where this miraging happens. But we've got the orange that we've done the original comparison on. But we also have the numbers that are listed above the actual turbine, you know, sort of like part way up it. So again, I've run a red line through the top of those numbers. And what do you know? It's the same thing. We are out of that circle of confusion, so we can do the mathematics on this. We can reduce them in angular size now, comparing it to the hub to the top of the numbers. And as they get smaller and smaller and smaller, again, the same thing happens. The same thing happens. They get pulled down towards the horizon. The horizon is such a narrow band looking at 0 degrees. It's such a very narrow band that the camera and your eyes can't capture all that information. It just gets squished into, well, just squished essentially. And this is what we're left with. Outside of the horizon, outside of 0 degrees, we can still make out the turbine top. So we can still see the blades cresting the water because they aren't at 0 degrees. They aren't getting that compression. And that's effectively what we're seeing. And this is what the turbine information is starting to give us, and why we've been told to stay away from it by certain people.
Hello, Mark. Excellent, Branty. Is there anything else that needs to be added?
No, that will be fine. Thank you very much.
I'm pretty happy with that. Excellent job. Really well done.
Perfect. How are you today?
What, me?
Yep, you.
Yeah, I'm very well, thank you. I'm looking after kids, so they've got the TV on in the background. Is it coming through, or is it okay?
Can hear it slightly echoey, but it's not too bad.
Okay.
Seems fine.
Very good.
You watch Ranti's presentation, or have you just joined from one of the Skype calls?
I've just joined the connection was taking me to a few days ago. The one you got advertised on YouTube, it's going back a few days.
Oh, really?
Yeah.
Oh, crumbs. Yeah. I'll sort that out. Just go on mute for a second.
So have you got any observations done yourself?
No, busy weekend with the family. Had to prioritise this weekend. What about yourself?
Yeah, well, it's been nice weather to go out and do it. So it's just the last few days I've been going in first thing in the morning. So I've been getting there at right, Arwen.
Hi, Owen.
Hello.
Yeah, I've been getting there at like 5 o'clock in the morning, and what I'm finding is obviously it's far too misty to see anything at that time in the morning.
Yeah, I tried at 10 o'clock in the evening. It was going dark, and this is what I got. Um, can you see that? Can you? Hide that bit. Can you see that, folks?
Yeah, just put it up for the audience.
Sorry.
Yes, it's up for the audience.
Yeah, right. Okay. That was at 10 o'clock at night. My camera struggled. That was the Isle of Man again. But there's quite a bit of refraction there. I wasn't getting down. It wasn't showing me low enough, although it was showing me the whole lot, from north to south.
We really struggle looking from east to west. I always struggle seeing the Isle of Man. Occasionally I get it, so perhaps maybe once every 12 or 14 days I'll see it. But for the most part, it's just out of my range. I can't. But I don't know whether it's something to do with the sun's angle at certain times to show it up. That's how I feel.
Yeah, well, that's directly west from me. So I'm thinking that in the autumn equinox, I should get sunrise right behind the Isle of Man. I'm just wondering whether I'm going to get a nice silhouette.
Well, it seems that you're seeing it you're looking from west to east, aren't you? So essentially you're looking the opposite direction to me. So you're looking into the sun, and you're able to capture the Isle of Man pretty much every time you go. You can always see it. And what distances are we talking there?
That's 35 miles away.
Right. Okay. Well, it's a bit farther. I've got to look, but still, I mean, I think it definitely has something to do with the.
But Sandra gets some lovely stuff at sundown, doesn't she?
Yeah.
So I'm going to be going out at the autumn equinox to try and get sunrise coming from behind. You follow what I'm saying there, yeah?
Yeah. I'm just trying to. All I'm trying to do is formulate some kind of knowledge as to why on certain days we can see it, why at certain times we can see it, and what's the relationship between the angles and stuff and sort of like try and get some kind of theory going. It's no good just putting it out there. Oh, I've seen the Isle of Man today without actually realizing why you've seen it.
Yeah.
Well, yeah, it's not that hard, really. It's a combination of air clarity and of how calm the water is, because the water will obstruct it in the foreground, especially if you're low to the ground, and the lack of air clarity in the background will also obscure it because it is very far away. So if both these conditions are right, then you will easily be able to observe it. It's pretty straightforward, I'd say.
I saw your hangout yesterday. I had to watch it back though because I wasn't actually at my computer when you did it.
Did you watch it backwards?
No, I played it back and watched it after you'd done it.
Ah, right.
So,
After the fact.
yeah, and after
yeah.
viewing.
Just
It was quite interesting what you were saying about the. Well, perhaps you could show it now. Actually,
What, my video?
well, not your video, but the image that you have.
Oh, the one that Chris Monk made. It's really an improvisation, but what I basically brought in my hangout is what if the globe Earth, if you assume that the Earth is a globe, then by our observations, it must be looming into a flat plane. Otherwise, you would never be able to see so far away under any circumstances, and you would always see the curvature. So if the Earth must be a globe, then it must be looming into a flat plane. But in order for everything to loom into a flat plane, there must be very persistent optical conditions present that will loom everything, bend everything into that flat plane, including the heavenly bodies observed at night, the star heavens. And what that would cause is, I'll click the picture. Where is it? Got so many pictures on my desktop these days. Did I even put it here? Anyway, what happens is that instead of a ball of stars spinning around us at a certain angle of the axis, it will, as the stars start to approach the horizon, they will, in fact, because of the looming bending everything upwards into that optically flat plane, that will start the side of the ball as it is approaching the horizon of the heavens, the stars, will actually start to wave out, decrease in speed to move with the looming effect, making it look like a net being draped over us rather than a ball, cutting off the horizon as we do actually get to see. And yeah, that is basically why looming is an optical impossibility, because we don't see that. Let me find that picture already.
Good stuff.
You got it up? No.
Good stuff.
I have no idea. I don't think I actually downloaded it. Maybe it's still there. I have to find it in the Skype. Yeah, here it is. I'm gonna have to relocate it. But there you go. It's of course not really how the constellations look and everything, but it is basically in imagining. So above you, you would see just the regular stars in accordance to their patterns, and as you approach the horizon visually, the stars will start to decrease in their angular velocity. The looming will set in, and they will start to converge at a line point into the distance, and basically getting in front of each other, making their almost like a line of light. A lot of stars that are sitting on that line, and as you would be watching it, it would be kind of looking like a net being draped over you, a net of stars that rests just above the horizon. That is what it would look like if it was all looming into a flat plane. Fortunately, that's not what we get to see at night. So, but you just ignore that part and everything will be all right. Everybody still here?
Yeah.
Good stuff.
I'm still here.
So I'm usually expecting to hear some interruption or something.
No.
All right. Anyway, looming. It's very complicated, and as I've been emphasizing in chat a lot yesterday and today, there's only one way to explain why you don't see curvature, because you don't. You never see it. We are always basically luring these globers into a trick to try to find the curvature, but you can't see it because it's optically not there. It can never be there because you always get to see that flat plane, and a couple of optical effects can trick you into believing that you can see the curvature, but it's optically impossible to see it because you always get to see the flat plane because it's all looming up there. It's all looming into a flat plane. Otherwise, you could never explain the super far distant observations, because that could never be possible under any conditions on a globe if there wasn't any looming present. So that's how that works. You just have to concede you can't see it curve because it's all looming. But yeah, then there is the inconsistency with the heavenly bodies. So
Hey, Chris.
you just have to close your eyes to that, and everything will be all right.
Well, Chris.
Morning.
Morning.
Hi, Chris.
Hey.
Hey, Chris.
I
Yeah,
did
Chris
a-
is in the Master B chat now, so
Right, okay. I did a bit of an observation this morning, Nath, if you present me. We're
Sure.
just talking about this looming side of things. Again, we're looking over at the buildings of Barrow, but they appear to be, how you would say, looming, or giving that effect of loom.
local looming.
Local looming.
Yeah.
And I'll just put that on mute so I can hear what I'm talking about. But yeah, I mean, we know that this isn't how these buildings look at all, and we know that the bottoms aren't looking like the sky underneath it, which is obviously being miraged down. So we have a clear mirage line going through the center of these buildings, and then the atmosphere is blocking out the bottom. So what it's doing is it's causing the sky to be miraged underneath the buildings before we can actually see the bottom of the building. So it's a blockage of atmosphere. It stops us seeing it, and this is how they would interpret looming. It's the same as with the boats. You know, boats on the water that appear to be floating in the sky. Again, that's the same thing. It's the sky is being miraged underneath it, and effectively makes it appear. It's an optical illusion. Makes it appear that the boat itself is floating, and that's what they would call looming. And they would have you believe that these buildings are being loomed up beyond the curve, which is why we can see them. It isn't the case. It's just that the sky is being miraged down, creating a fake appearance of loom, and that's what it is. If you think about that, this chimney as well, we also know that the height of this chimney isn't that tall. We know that the top of it ends around about where my cursor is here, and this is just a mirror image of the chimney above it. So proof in evidence in this one image right now that you're looking at that destroys looming, because this chimney isn't that height, and obviously that's the sky being miraged up, and that's a complete reflection of the top of the buildings.
So what you've got in the chimney, if you just go back to it, so you will have the same effects. You know, it will be miraged down below itself, but because it's a tall stick, it doesn't look like it would be any different. In other words, the mirage looks identical to the thing above it. You know, you can't tell the difference, right?
Yep.
So that's the effect you're getting with these wind turbines. Everything does it if you can see this band. It must. It's got a... This is just the effect of a reduced viewing angle. That's the effect that happens. That's what Zachary Sabala has shown. And obviously he's considerably closer. You know, he's a matter of inches above the water rather than a matter of feet over a considerably further distance. But the effect of the reduced viewing angle is the same. And the net effect of the miraging with it going below itself and the horizon dropping, all of those things that Zach demonstrates are what we are seeing in these pictures. You know, and it's not like he's going miles and miles and miles. He's doing it in a warehouse. But the effect's the same in small scale. You can reproduce it because he's closer to the ground. Therefore, the reduction in viewing angle is considerably more severe at a shorter distance. So you can essentially replicate it in small scale by getting the camera right next to the ground. And that's precisely what we're seeing.
And just to sort of like clarify some other things as well, is that we know there's buildings beneath this chimney stack. We know there's buildings. We've seen it many a time from my observations, but we can't see them because of this water layer. Pete Shea makes reference to this particular water. I forget what he's called it now. The angular water layer or something, and that's what it does. It causes a reflection of the object above it, and that reflection, before it gets to, you know, it kind of blocks what you're seeing. So those buildings will be behind it, but we can't penetrate through this layer, this water layer.
Have you got a similar view of that on a different day in different atmospheric conditions?
Yeah, I've got loads of these.
Yeah, I'm sure you have. Can you show us one? One of the better ones when there's very little refraction.
What do you mean better? That was brilliant. Shows the effects of refraction.
You know what I mean. We just need to get a succinct way of shutting people up and say, look, there you go, and there you go, end of story.
There we have the tower.
Yeah.
Here we have the building next to it.
Hold on. Tell us the elevation.
1 foot elevation on this. A single miserly foot above actual sea level at this time when I took this image. And we see all of the, shore to shore, basically. Shore to shore.
And where's the chimney?
Chimney's here.
Oh, that, right, okay. And that's what you were showing us in the previous image?
Yes, yeah. Might have a better one to show you from a different angle again. Be one of these ones up here. Ah, here we go. So again, there's the chimney.
Yeah.
And there's the building next to it. So the fact that we can't see the building in today's footage shows that we're only seeing this tiny portion of the top part. So let me crop that out. If I just crop that part out there, effectively we're only seeing that, or because otherwise we'd see the building next to it. So if I crop to selection there, and then we know that that's all we're seeing, but we look on today's footage and look at the difference. If I take a print screen of that, and now we compare that. So I paste that in there, and we copy this. Yeah. See what you can see.
That's brilliant.
So effectively that building, and let me just crop that out to there. So that building that we saw in the other image should be here. It should be in this location there, but we can't see it because this reflection of this chimney is starting there. So it's reflecting down, and this atmosphere is effectively blocking out us seeing anything.
Yeah. So it's not the horizon of the water or any curve. It's just an optical illusion, isn't it? It's
just blockage, is what it is. So if I like take this back, and then I crop this part out, this is what we should have seen. So let's crop that out. There, image crop selection. I'll paste it in here, hopefully. And let's make it a little tiny bit smaller. So something like that, tiny bit smaller again. Got to match up to that. So yeah, something like that. Effectively, this building is in this blockage area here. So let's get it to scale so we've got it right. So like that, I would say, isn't it? That's probably more accurate. And that's all we're seeing. And obviously you've got your fake waves underneath. I keep calling them fake waves because that isn't real waves. And keep going on about it, and you guys are going to get this eventually. But this is fake waves. I mean, it's like that there is not a wave. Trust me, it's not a wave on the horizon. And these, the two lights would be real waves. You see through them. You see through them. The real horizon is round the bottom here. So yeah, so going back to this, so the looming side of things, yeah. So we was talking about looming, weren't we? So this is the appearance of looming. So if you're looking at a boat on the water, this is what you'd see. You'd see the sky reflected underneath it. The boat would be floating in thin air, and you'd think it was looming. And that's where they've got this idea that things can be loomed up, which is just nonsense, really. It's just the reflection of the sky underneath the objects you're looking at.
And I would argue that you could only have these effects on a flat plane. In other words, none of these effects with these actual mirages running full lengths of images that are further and further into the distance, that can't happen on a globe. You need flat surfaces for these angles to work out mathematically and actually quantify how it all works. Now, while we haven't done that, I'm absolutely certain it is impossible to bring a mirage back and get a mirage to loom around the curve. It's just utter nonsense.
Yeah. Because you'd have two effects going on there. You'd have the looming coupled with the miraging, so the mirage would have to be a mirror image of the loom that isn't really there, because that loom isn't there, it's a hologram. You'd be getting a mirage of a hologram, which is impossible.
I've got Philip in the chat says, have you got a citation, please? Well, I'm actually referring to you, Philip. So you did a model for us with ray tracing, and you were unable or incapable of actually modelling the mirage effects that we saw in the images. So you were talking about refraction a lot and the mathematics you applied, but you didn't actually manage to model the effects of refraction. That's the point. So unless you've managed to do that, which you're welcome to join once I sort the link out, which currently doesn't work. But yeah, with that, I'm going to say first and foremost, a huge, massive, enormous thank you to all of the live audience for tuning in and hopefully sharing this debate. And of course, a massive thank you to all of the debating panel for making this debate possible. If you hated the show, you know exactly what to do. But if you like the show, maybe consider sharing it with a friend or subscribing if you've not done so already. I've been Nathan Oakley, and I'll see you all in the next video. I'm going to say bye-bye. Bye-bye.
Oh, what a day! What a lovely day!